All right, so here is where we left off. We were looking at the equations on page 9 for friction and the different types of friction, static friction and kinetic friction. So today we're actually going to be skipping ahead. We're going to skip some of the practice problems that are in between. Y'all have already done 11 and 12. We're going to skip all the way to page 17. And we're going to do a few friction practice problems. And then we're going to do what's called a derivation, where we are going to derive. Okay. We're going to derive an equation for the challenge problem at the bottom of page 17. And that is going to be what you need for the lab. So the actual lab is going to be just a small part of class today, but we really need to cover using these friction equations before you're going to be comfortable to walk through and do all of these steps. All right, so top of page 17, we have a 20 kilogram trunk pushed across the floor to the back of a moving van by a horizontal force. If the coefficient of kinetic friction between the trunk and the floor is 0.255, what is the kinetic friction acting on the trunk? So first thing we always need to do with these problems is we always need to draw a free body diagram. And because the problem says that this is something that is resting on a floor, we want to draw the surface. All right, that's going to help clue us in to the fact that the problem says specifically that there is friction, but whenever we have a surface, we always have what kind of force? Normal force. So it's not natural, it is normal, but I know what you mean, and that's okay. And the good news is, Antonio, that I'm not going to ask you to write out the word, so you're just going to abbreviate it FN anyway on a free body diagram. So even if you did think it's natural force in your head, it's still going to be FN. All right, so tell me, what forces do we have on this trunk?
Gravity.
Gravity. That's always the right answer. So we have gravity and we have normal force. Because it is on a surface, that means we have a normal force. What other forces do we have? Okay.
Friction.
So Carter says thrust. Thrust is probably not the best term to use here because thrust typically involves air. So like a rocket engine or a jet engine has thrust, but we could call it an applied force, or we could call it F push, something like that. This horizontal force that is mentioned in the problem, we have to account for that. It doesn't tell us in the problem what direction that horizontal force is being applied. So typically that means we just assume that the push is in the positive direction. So I'm going to call this one F applied. You could call it F push. You could call it F shove. You could call it F horizontal because it says it's a horizontal force. As long as what you call it makes sense, it doesn't have to have a specific name. Did you have a question, Antonio?
No.
Okay, just stretching.
No, I think I have another force.
You have another force. Okay, what other force?
Friction.
Friction.
Nice.
What direction will friction be? What'd you say, Ava? Opposite what?
Opposite of the
Opposite of the applied force. So friction always moves in the opposite direction of the velocity. And in this case, it is the opposite direction of the applied force. But if there's going to be some more complicated scenarios where friction is not always in exactly the same direction as the applied force, but friction is always opposite the direction of the velocity, and friction is always parallel to the surface. So what kind of friction is this going to be? it's going to be kinetic friction. How do you know that, Carter?
Because it says what is the kinetic friction after.
All right, so that's good reading there. Sometimes it's as simple as that. What is the kinetic friction? How else do we know?
Is it because it's in like constant motion?
Because it's in motion, it is kinetic friction, okay? What would it be called if I was pulling on this trunk and it was not moving? What kind of friction?
Static.
Static friction. Close, Will. You'll get it.
That was blue.
Okay,
Just practice.
so let's look at what do we know about these forces. Okay, so whenever I analyze forces to do any math with them, I'm gonna follow a couple of steps. First of all, we need to recognize that forces that are acting in the y direction, up and down, have absolutely nothing to do with forces that are acting in the x direction, forward and backwards. Just like when we studied two-dimensional velocity and acceleration with projectiles. The motion in the y direction and the motion in the x direction are completely separate. Same thing applies with forces. So, what do I know about the force of gravity and the normal force? What can I assume?
They cancel. They equal each other
They're going to equal each other. Why do we know that?
because it's not levitating and it's not crushing the ground.
It's not crashing through the surface, and it is not levitating. So this trunk is being pushed across the floor. So we know that this is how we're going to write it. We're going to write the letter sigma, which means sum. It's kind of like an E, but that's what it looks like. The sum of the forces in the y direction, when I add together those forces that are up and down, what are they going to add up to equal? 0. Because one is going up, one is going down, and they're going to be equal to each other in magnitude. All right, so the sum of the forces in the y direction is going to be 0. What are those forces that are acting in the y direction?
Normal force and gravity.
So normal force is up, so we'll call that positive. And then we're going to subtract the force of gravity,
And that should be 0.
right? When we add them together, it's going to be 0. Neither one of those forces by themselves will be 0, because if you have 0 gravitational force and you're sitting on a surface, then you have no mass. So it's impossible to have 0 force of gravity if you are on a planet at all. Carter?
Would you make the force of gravity still negative even though it's to the right of the negative sign, or would it be positive now?
So because it is pointing down, we subtract. If we had two forces, and we're going to see a few of these, if we had two forces that were pushing the same direction, we would add them. But if we have one that's in the positive direction, one in the negative direction, we subtract. Yes?
If you had like the ground and then like a box and a box on top of it,
Mhm.
could you have like two normal forces because like the box pushing up and the other box pushing down?
There would be a normal force between the surface and the first block, and then a normal force between the first block and the second block if you had a stack of blocks, yes. We typically don't do much of those. I can't think of any problems that we'll do in this class, but we do a lot of that in AP Physics, where we have boxes, I'm going to push this box that is here, then that box is next to another box, and it's going to push, and, how much force does box A push on box B and all that. Okay, so if Fn minus Fg equals 0, what can I say about Fn? That's going to be equal to what? Fg. All right, simple math. Now we have an equation. We know that Fg is equal to something. Look back in your notes when we talked about the different types of forces. First of all, what is Fg?
Gravity.
It's the force of gravity. What is that the same thing as?
9.81.
No,
Oh, you're
Would
right.
it be
No.
the weight?
it's the weight. It is the weight of the object. So you have a formula on the page where we wrote out all the different types of forces in your note packet. You have a formula for Fg. Tell me what that is.
Equals
Equals mg. And what is little g?
acceleration due to gravity.
The acceleration due to gravity. All right, so the equation to find the force of gravity, which is the same thing as weight, is mg, mass times acceleration due to gravity. And we're very familiar with the acceleration due to gravity because we used it in kinematics. So if Fg equals mg and Fg also equals Fn, what can I say about Fn? Equals mg.
That is a certain law, I forgot what it was.
And you know what? The cool thing is we don't care what those laws of math are called. All right? So we care about using them, and we use them a lot, but I couldn't tell you what the name of that mathematical law is. All right, so why do we need to do all of that? Because we need to know what the normal force is in order to calculate the value of friction. So we have a formula. We're looking for kinetic friction. Kinetic friction equals what? We have a formula on that same page in your note packet that gives us a formula for how can we calculate the value of friction.
Oh, wait.
Do you want to look it up and tell me what it is?
Oh my goodness, I remember this.
A friction.
Equals,
Yeah.
Equals, mu k times F.
Fn. All right, so remember mu, and this is mu k. Mu looks like a lowercase u, but it has a great big tail at the beginning. All right? So it's a weird thing to say. It's a weird letter, and unfortunately, it's, every physics student's favorite thing is just to use the term mu. All right, so mu is the coefficient of friction. All right, so mu k times the normal force. When we multiply those two things together, that's going to give us the value of friction, of kinetic friction,
Wait, kinetic friction, I forgot, is like when it's actually moving.
when it's moving.
Okay.
And so Carter did a great job of reading the question and telling us we want to find kinetic friction here because the problem is asking for that. But we also know that it's kinetic friction because it is being pushed. All right? So kinetic friction, now we've got an equation. Actually, before I do that, mu k times the normal force is going to equal mu k times what else? What did we say normal force was equal to?
mg.
Mg. So mu k mg. So now I have mu k, that was given to me in my problem, that's 0.255. I have m, which is 20 kilograms, and I have g, which is 9.8 meters per second squared. Now I can plug in some numbers. So we have 0.255 times 20 kilograms times 9.8 meters per second squared. And what do we get for the value of friction?
Wait, it's 0.2251.
0.255.
Oh, 0.25.
That is the coefficient of kinetic friction. 44 point, 44? I got 49. Let me grab my calculator. 0.255, not 0.225.
I got 49.98.
Good.
Wait, so I don't get it.
You don't get it.
It's asking for the coefficient of kinetic friction. What
Yes.
is the coefficient of kinetic friction?
Okay.
FK?
No, it's mu. Coefficient of kinetic friction is this mu k right there.
So, like to put that into words, instead of like saying UK, you could just say the coefficient of.
Uh-huh.
Okay.
Yes.
Is
And
that somewhere in our notes?
yes, it's on that same page.
Okay.
Okay? on that page that we wrote out all those notes about all those different types of forces has several equations on that page of notes that you're going to need to refer back to. Once you use them enough, they're going to become second nature and they're going to be a lot easier to recall. But what do you notice about that coefficient of kinetic friction, that 0.255? What is it missing that we normally have next to every single number in physics? There are no units for a coefficient of friction. It is quite possibly the only number that we will ever come across in this course that is allowed to be naked. All right? So that's the only number that I can think of that we will use this entire year that does not have a unit attached to it. All right? Because it's just a ratio. It is a ratio of the amount of friction to the normal force. And so amount of friction is measured in newtons. Normal force is measured in newtons. When you have units of newtons divided by newtons, they cancel each other out and you're just left with a number. All right, so all it is a ratio. All right, let's do number 2. And then we'll get to the fun one, which is question 3. And that's going to be kind of what your lab is going to be all about. All right, question 2. A 25 kilogram chair initially at rest on a horizontal floor requires a 165 Newton horizontal force to set it in motion. All right, so when we have something that is initially at rest and it requires a certain amount of force to get it started moving, what kind of friction are we dealing with? Static.
Kinetic, so like when it's already.
Kinetic is once it is already moving. So, do you remember we said when you are trying to slide a big, heavy piece of furniture across a room, it takes more force to get it started moving than it does to keep it moving once it is moving. All right, same thing if you ever ran out of gas with your car and had to get a bunch of buddies to push your car off to the side of the road. It takes more force to get that car to start moving and less force to keep it moving once you have you and your buddies pushing it. All right, once the chair is in motion, a 127 Newton horizontal force keeps it moving. So what kind of friction are we talking about there?
That's kinetic.
That would be kinetic. Okay, so we have 4 different questions that are being asked here. First one, what is the weight of the box? Well, before we do anything, before we do any calculations, we need to draw a little free body diagram. So is this on a surface?
Of what box?
I'm sorry?
Of what box?
Of what box?
It says, what is the weight of the box?
Oh, you know what? That is a typo.
Oh, okay.
Chair. All right. You know what? I think I've used this same question for probably 6 years, and I haven't caught it. All right, so it's on a surface. Anytime that the problem tells us there's friction, that's also telling us that it's on a surface. Because you can't, well, you can, it's called air resistance, but we're not going to do any calculations involving friction unless there's a physical surface. All right, we're not going to do anything really calculating with air resistance because it's a lot more complicated. So tell me, what kind of forces do we have acting on this chair? So we have gravity and normal force. So F push, that's a good way to say this because it says, you know, it requires a certain amount of force to set it in motion. We could call this F applied, we could call it F push. Really doesn't matter as long as we know that it is a shove or a push in some direction. We could also say that it's going to the left if we wanted to. It's easier when the forces are not equal. It's easier for whatever our bigger force is. If we know that the object is accelerating, it's easier to say positive is the direction that it is accelerating. But we could say that the push is to the left and friction is to the right. And then we're going to have, what is this force back here going to be called?
Friction.
We're just going to call it the force of friction, because we're also dealing with two different kinds of friction. So F, little f, big F, little f, is what we would label something if we're talking about just generic friction. So it could be, we're going to do some calculations that involve static friction, and then we're going to do calculations that involve kinetic friction. So we're going to be dealing with both, but we need to label it something, so we just call it force of friction. All right, so what is the weight of the chair? How am I going to find the weight of the chair for question A?
Turn it to newtons.
I need to not turn something into newtons. I need to calculate something that will end up being newtons. How do I do that?
Oh, kilograms per meters per second squared. Is that the formula?
So what is the formula? We just wrote it in the last problem. Fg is our weight. What does that equal to?
Oh, mass and gravity.
Mass times the acceleration due to gravity. Whenever we're calculating a weight, we have had kind of drilled into our heads from kinematics that acceleration is always negative 9.8 meters per second squared. All right? Whenever we're calculating the value of a weight of an object, though, we never use the negative, because we are indicating with the direction of the arrow what direction that weight is pointing. All right? So we never include mass times negative 9.8. We just calculate it as mass times 9.8. All right, what is the mass of my chair?
25 kilograms.
25 kilograms. And G is going to be 9.8 meters per second squared. So what do I get for the weight of this object or chair?
245.
Okay, and what are the units?
Newton.
Newtons, good. All of our forces are going to be measured in newtons.
So that's how to change any like weight into newtons.
So mass is going to be in kilograms, and then mass times the acceleration due to gravity will be newtons. And remember we said a newton equals 1 kilogram times meters per second squared. So we have mass, which is in kilograms, times acceleration due to gravity, which is in meters per second squared. So that's why a newton is the same thing as a kilogram times meters per second squared. If you forget on a test, totally appropriate for you to just write kilograms times meters per second squared, because it's the same thing as a newton. All right, but all of our forces will be measured in that unit of newtons. All right? What is the normal force? Well, I can look at my diagram and I can figure out pretty quickly what the normal force is.
Oh, 245.
It's going to be 245, and it's going to be pointing upward while my weight is pointing downward. All right, how do I know that the normal force and the weight are the same?
Because the formula,
If it's not Fn equals Fg.
Okay, but Fn does not always equal Fg. Fn is not always going to be the same as the weight,
It's not crashing down.
because it's not crashing through the surface and it's not lifting up off of the surface. All right, so the chair is sliding across the floor. All right, and it doesn't specifically say that in this problem, but we can assume it because it doesn't say that the chair is being lifted. And it does say that there is friction. So if there is friction, that means that whatever is being moved is in contact with the surface. All right, so all the forces going up are going to add up to equal all the forces going down. And right now we only have those two forces, weight and normal force. All right, part C says find the coefficient of static friction between the chair and the floor. What formula should I use to calculate the coefficient of static friction?
Fn equals mg. Oh no. Wait.
Okay,
Fs is less than or equal to ms Fn.
okay. So,
Yeah.
what you just said was Fs, static friction, is less than or equal to mu s times Fn. All right? So, do you need me to back up a little?
Oh no.
Okay. So here's our formula. That's on that same page with all the other notes about the types of friction. How can I rearrange this to solve for mu?
Divide by Fn.
Divide by Fn. So mu is going to equal static friction divided by the normal force. And the problem, so this right here, this equation that says Fs and mu s Fn, that's a less than or equal to, because remember we talked about how static friction is kind of like normal force. If I push on my water bottle with less force than the maximum static friction, my water bottle isn't going anywhere. All right? I have to push the maximum amount of static friction before it will start to slide across the floor. So, in order for me to calculate this, the problems kind of assumes that this is the maximum amount of static friction that can be supported here. So, if mu equals the maximum static friction divided by the normal force, then I just plug in some numbers here. So we have 165 newtons divided by the normal force, which is 245 newtons. And what do we get for the coefficient of static friction?
Point 0.67.
0.67. I know, I did not plan that. I didn't even think about that and came up in my last honors physics class. All right. Yeah, wouldn't it be cool if 41 was the next one? All right.
That's subtle foreshadowing.
Actually, no, because I didn't write these problems, and I've used some of these same problems to teach with for 6 years now. So obviously this predates the whole 6, 7. All right. Part D says find the coefficient of kinetic friction. So if mu s equals Fs over Fn, what do you think mu k is going to equal?
Wait, 0.67 equals what? Oh.
That is the coefficient of static friction, mu s.
UK.
Oh.
What do you think mu k equals? What do you think, Carter?
I have a question.
Oh, okay.
Why isn't there a unit sign?
Why isn't there a unit? Is because we have newtons divided by newtons and it cancels. So this is the only number that I can think of that we're going to use in physics that does not have a unit.
So any coefficient cells.
Any coefficient of friction will be unitless, just a number, because it's just a ratio. Yes.
Is it mu k equals fk over fn?
Yes. And what does Fk equal?
It's 127.
So that's going to be 127. So that's the amount of static friction divided by the normal force, which is 245 newtons. Again, newtons are going to cancel. And what do we get for mu k? 0.51. Or, yeah, we could say 0.52. All right. How are we feeling about those problems? They're not too hard, right? All right, so now we're going to do the challenge problem. So, let's look at my little setup here. We have a block and we have a wooden surface. So, I want to be able to calculate the coefficient of static friction between my block and my wooden ramp surface, okay? Now, how could I do that? First of all, the thing that we need to keep in mind is that the coefficient of friction only depends on the two surfaces. It does not depend at all on how heavy my block is. All right, so the coefficient of friction does not make a bit of difference how much this weighs or how much mass it has. It is only the two surfaces. So if you think about a hockey game, the rubber puck and the ice, they have a very low coefficient of friction because when you slap that puck on ice, you want it to go. All right? But something that has maybe sandpaper on it or something that has grip, like the what do you call this? The boot of a water bottle that has some grip so it doesn't slide. I don't want my water bottle to slide. You know, I might knock it or something like that. I don't want it sliding across the table. So the boot has a much higher coefficient of friction with other surfaces than that hockey puck does on ice. So how could I determine, and we're not going to do kinetic friction because it gets a little bit more complicated, but how could I determine the coefficient of static friction between this block and my surface here, my wooden ramp? Now, if I had a force probe, which I do have, but I'm not going to let you use. If I had a force probe, I could hook up a force probe to the hook on my block, and I could pull, and right when this block just starts to move, I could see what does the force probe reading say, and that's the amount of force that it takes to overcome static friction. That would be too easy, because then all I need to do is read the probe, take the mass of the block, boom, I've got the normal force, I've got the amount of friction, I can calculate coefficient of static friction just like I did in problem number 2. We're going to do it a little bit low-tech way. All right, so here is the scenario. I have my block and I have a ramp, and I'm going to slowly lift my ramp, and I'm going to stop right at the angle at which my block just starts to slide down the ramp. All right? So you guys are going to be doing this with, we're going to have 4 different groups, so we're going to have 4 different surfaces that we're going to test. So you're only going to be responsible for doing testing and calculations with one surface. But we're going to look at how we analyze this type of problem. Because if I didn't have this handy dandy protractor here and all I had was a meter stick, I could use trig. I could measure the length of my ramp and I could measure the height of my ramp right when the block starts to slip. And my little string is getting stuck. You can see that this is low tech. But if I know the length of my board and the height when it starts to slip, guess what? I got a triangle here. I could calculate angles and I could find all of that information. So let's draw this diagram here. So we have a box sitting on a ramp that just begins to move when the angle of the ramp reaches 22 degrees. Our goal here is to calculate mu s, which is the coefficient of static friction. So here is my ramp, and here is my block, or box, or whatever you want to call it, object. What forces do we have acting on this object, this block or this box?
Friction, normal.
Okay. Friction is going to be the absolute last thing that we ever label. What should be the first thing that we label? Gravity. What direction is gravity?
Diagonal left.
Always straight down. Always straight down. All right? Because gravity is a measure of how much the earth is pulling on this box, okay? And FG, we said, remember, was mg, all right? So I'm just going to write that here because that's going to help me in a minute. All right, I know that my angle, by the way, is at some angle theta. And for this, once we get to substitutions, we're going to substitute 22 degrees. What other forces do I have on my box? Normal force. And yeah, just say FN. What direction does the normal force act?
Opposite to
Oh, it's diagonal left. It's diagonal left.
So the normal force is always perpendicular to the surface. So you might be saying it's actually diagonal to the right, not diagonal to the left. So normal force is always perpendicular to the surface. I know that that's what you meant, but you were saying it incorrectly. But diagonal right is not precise enough. Perpendicular to the surface is really what we're looking for because it's at a 90-degree angle to the surface, okay? What other forces do we have here? We're going to have some friction. What kind of friction? Static. How do we know it's static friction? Just begins to move. So any angle lower than 22 degrees for this scenario, it's not going to move, so that's static friction. Now, what direction would static friction be?
To the right.
parallel to the surface, they're going to the left.
Parallel to the surface.
Perpendicular.
Parallel to the surface, but going the opposite direction of the way that the block wants to go. It's not moving yet. We said that it's the opposite direction of the velocity, but this block is not moving yet. The static friction is preventing it from moving. But what direction does the block want to go? The block wants to go down the ramp. So static friction is going to oppose it up the ramp. So this is static friction. All right, so herein, what do I have? Let's look here, okay? So I have my handy dandy little X and Y axis, homemade, of course. So here's my X and Y axis, all right? If I look at this and I put my X and Y axis up on my forces like this, what do I see? How many forces do I have? 3. How many of them are going along the X or the Y axis? 1. Okay. So here's what I'm going to do to make my life just a little bit easier. I'm going to take my axis, and instead of looking at my axis this way, I'm going to tilt my axis this way. Now, how many forces are acting along the axis? And how many forces are at an angle where I'm going to have to split it up into a triangle? 1. So whenever we analyze situations where we have an object on a ramp, we tilt our axis. How much do we tilt our axis by? The same amount as the angle of our ramp. So if you're looking at a 15-degree angle, then we're going to tilt the axis 15 degrees. Okay? So I'm going to draw the new axis, and then we're going to have one triangle that we need to break up. All right? So here's my x-axis, and here's my y-axis. So we see that on our new tilted axis, normal force is straight up, static friction is straight to the left, and the force of gravity is at an angle. Well, whenever I see things at angles, as a good physics student, I see triangles. So I'm going to break this force of gravity into a triangle. So I have a part of my gravity that is going down like this, and I have a part of this gravity force that is going like that. All right? So if I have a triangle, so I have this, this, and this. This is my force of gravity, which equals mg. What part of the triangle is my force of gravity? Remember, we have opposite, adjacent, hypotenuse. Which one is my force of gravity?
Hypotenuse.
That's going to be the hypotenuse. Okay? So this is the hypotenuse. This right here is my angle theta, and this angle theta is the same angle as the angle of the ramp. Okay? So with reference to this angle, what would this side of the triangle be?
Adjacent.
Adjacent. So which trig function covers the adjacent side of the triangle? So which one has adjacent in there?
Oh, adjacent.
So I have the, if I'm looking at this side, I know the hypotenuse, and this is the adjacent. Which trig function has adjacent and hypotenuse? Cosine.
Wait.
All right? Yes.
Oh wait. Give me a second. And then. Okay, never mind.
Okay. So I'm going to write it up here in just a second, but I wanted to do it over here first. All right? So this part of my triangle is the hypotenuse times the cosine of my angle. So this side right here becomes mg cosine theta. What is this side of the triangle? Opposite. That's opposite. Which trig function relates the opposite side of the triangle with the hypotenuse? Sine. So the sine of this angle equals this side over the hypotenuse. So this side right here becomes mg sine theta. So now I'm going to go ahead and label these. So this is mg times cosine of theta. And this vector is mg times the sine of theta. So now, instead of just four forces that are up and down, that are, very simple because we have a horizontal surface like what we saw in problem number 1, we have tilted our axis a little bit. And now, guess what? We still have just 4 forces. We have normal force going up. We have mg cosine theta pointing down. We have static friction going to the left, and we have mg sine theta pointing to the right. All right, so now we still have just 4 forces, but instead of being like this and very simple for us to think about, we have just tilted them like that. Okay? So, remember that I have to keep separate my forces that are in the x and the y direction. I always start by looking at the forces in the y direction, all right? Because that's where the normal force is almost always going to be found, all right? And the normal force, we need to find out what is a normal force equal to, because then we're going to substitute normal force into something for friction down the road. So, I always start with some of the forces in the y direction. What are the forces in the y direction going to add up to? So when I look at normal force
0.
and mg cosine theta, these are going to add up to equal what?
0.
Why? Why do these forces up and down always add up to 0?
Because
Because they're the same.
Why are they the same?
Because if it wasn't, like, it'd be crashing.
So if I look at my block and I watch my block, so keep in mind now on my ramp, let me try to do it this way. All right, my axis is now tilted. So my axis goes up. All right, so did you see the block go this way or that way? No, it didn't. It didn't come off of the ramp. It didn't crash through the ramp. So the sum of the forces in the y direction, when I add up those two forces in the y direction, they're going to add up to equal 0. Okay? What are those forces called? One of them is normal force, and it's positive. The other force that is along the y-axis is mg cosine theta, and it is negative, so it's pointing down. So normal force minus mg cosine theta. So if Fn minus mg cosine theta equals 0, what does Fn equal to? Fn minus mg cosine theta equals 0, then Fn equals mg cosine theta. So we're going to kind of pause with that because we have derived an expression where we can figure out what is our normal force equal to. So now I need to look at what are the forces in the x direction. And because we're dealing with static friction, the sum of the forces in the x direction will equal 0
Wait, is
when the
that E
block just starts to slip.
Is that E like the fancy E?
That is, yes.
Okay, but we don't have to do it like that.
Yeah, so sigma
Okay, it's like that.
is like that, but it's totally fine for you to just kind of write it like that.
Okay.
Kind of like a sideways W. All right? All right, so the forces in the x direction are going to add up to 0 right up until the part when the block just begins to slip. Okay? So, sum of the forces in the x direction are going to equal 0. What are those forces in the x direction?
Oh, mg sine theta.
Mg sine theta
And FS.
and Fs. It does not matter right now which direction we call positive and which direction we call negative. But we're going to get into some problems where it makes more sense for the math for us to call down the ramp as the positive direction, okay? Because that's the way that the block wants to go. All right, sometimes you're going to see a problem where somebody shoves a block and gives a block some initial velocity and it goes up the ramp and then stops and then comes down the ramp. And then we have to just pick which one do we want to be the positive direction. But if we're just talking about the block just wants to slide down, doesn't matter which one we call positive, but it, you know, we could go either way. So what is static friction equal to? If mg sine theta minus Fs equals 0, then Fs equals mg sine theta. Okay? Now, I have another expression that I have learned and I have used today that says that the maximum static friction is going to equal what? What equation do I have?
Less than or equal.
Yeah, so it's the less than or equal to, but when it's at its max, it's going to be equal to
Equals to
mu s
Fn.
times Fn. Well, guess what? I just derived an expression for Fn a couple lines above where I am now, so I'm going to substitute for Fn. So maximum static friction equals mu s times, what does Fn equal to?
Fn mg equals
Mg cosine theta. All right, so if Fs equals mg sine theta and Fs equals mu s mg cosine theta, what can I say about mg sine theta and mu mg cosine theta? They're equal to each other. All right, so if this equals Fs and this equals Fs, then that means that this equals that,
It
right?
doesn't matter that it says max.
No, because we're assuming that we're at the maximum static friction here, all right? So I just wrote it this way because our formula says less than or equal to. But when we're at the maximum, right when the block starts to slip, then that means there is enough force going this way that is going to match and just start to overcome this force, okay? So I can say that since both of these expressions equal Fs, that mg sine theta equals mu s mg cosine theta. Is everybody with me?
It's
Uh,
kind of like,
this is just math. This is just algebra. And it's hard because it's unfamiliar. And it's hard because we have to look at things along axes that look different from what we are used to seeing. All right, so now I have this expression. Remind me again, what is it that I am trying to solve for? What's the whole point of this
at a
problem?
distance, or what is that?
Mu s. What is mu s? What is it? What is it called?
Oh,
What is mu s?
static.
What is mu s? Look back at your notes if you need to.
FN.
No, I'm not asking for a formula. I'm asking you to tell me what is mu s. What is it?
Friction.
Coefficient of what kind of friction? Static friction. Okay, so what I need to do is I need to get that mu, the coefficient of static friction, on one side of the equal sign, and I need everything that's not mu on the other side of the equal sign. But before I do any of that, I see some stuff that shows up on both sides of my equal sign. So what can I do to those things? I can cancel. What can I cancel? M and G. Because mg shows up on both sides of my equal sign.
And then would it be the 22, or you can't cancel it?
We're not there yet. Okay,
Oh, so then you just do sine.
so we want to get mu all by itself. Let me just kind of continue up here. So we have sine theta equals mu s times cosine theta. So mu is going to be sine theta divided by cosine theta. But I can simplify that even more. All right? How would I calculate sine of theta if I was in a geometry class and I just had a triangle? What would sine of theta equal?
Oh, also my
Opposite over hypotenuse. Okay, so I'm just going to write this out. Opposite over hypotenuse. What would cosine of theta equal?
adjacent over hypotenuse.
Adjacent over hypotenuse.
Oh, do they cancel out?
Guess what? My hypotenuses cancel out. And so what I'm left with is mu s equals opposite over adjacent. And what trig function is that?
Tangent.
Tangent. So mu s is going to equal the tangent of the angle theta.
Would you have to do that, or could you just put once we get to the part when we plug in 22 degrees,
Mhm.
could you just do sine of 22 divided by cosine of 22?
You'd get the same thing. But this right here, this is called a derivation, where we have derived an expression for how to calculate mu s for a situation where we have a block or some surface on a ramp and the object just starts to slip as we raise our ramp angle up to a certain point. All right? Do we need to know how much mass is in this block in order to do this calculation? No, we don't. The mass of the block makes absolutely no difference because the mass cancels out. So now over here, I can come over here and say, okay, so mu s for this situation, when theta equals 22 degrees, mu s is going to equal tangent of 22 degrees. Go ahead and make sure that your calculator is in degree mode and tell me what is the coefficient of friction for this scenario.
0.4.
Give me more digits than just 0.4. 40 or 404. All right, so for this scenario, this is the coefficient of friction for these two surfaces. If I had sandpaper on this box, my coefficient of friction would be higher. If the box was coated with ice on the bottom, the coefficient would be less. Or if it was coated with something that is slicker, then it would be a lower coefficient of friction. Okay, so here's what you guys are going to be doing. You are going to, let me pull up this lab, and the assignment for the lab is in Canvas. Do we have more than 10 minutes? Awesome. You guys have 25. All right. So here is the rubric for your lab. It's in Canvas. I don't care if you give me typed or handwritten, does not matter. A combination of both is okay too. All right, so you're going to tell me what is the purpose of this lab? What are we trying to accomplish here? And I'm going to give each group, so Andrew, would you mind working with Carter? So we'll have 4 different groups, and each one of you is going to have a different surface on your block, and you're going to have a ramp just like mine. All right, and you're going to just slowly lift that ramp and then measure the angle, right? This is a super, super low-tech lab. So the measurements that you get might not be super precise. You might have one angle that is like 25 and then the next time it's at 35. Try to take, and I said 3 is minimum here. I would recommend that you get 5 and keep trying until you get 5 that are reasonably close together. All right, so you need to identify the surface. So your surface is either going to be sandpaper and wood, or a copper surface, and wood, a smooth gray surface, a fabric covered surface, something like that. You don't need to know exactly what it is. Then I need you to write out the procedure. Does not need to be in complete sentences. A numbered steps or bullet list is fine. I need you to give me the data, a chart, a list, something, as long as it's neat. I don't really care how you present your data. And then I need you to draw the diagram, just like we drew in the class notebook before. I said at least 3. Let's do 5 trials. And then I need you to write out the derivation, just like we just did in that last problem. So derive an expression for mu s with no numbers. And then when you go to calculate the coefficient of friction, second to last step, take your 5 trials, take the average of those angles, and calculate the coefficient of friction one time, not 5 times, just one time with the average angle that you found, okay? And then write about what can you conclude, what would your results be if you had a more coarse material, what would your results be if you had a smoother material. All right, so the rubric is posted for you in Canvas. I recommend that you look at that. This is how I'm going to grade the lab is I look at each one of these things. Did you do everything that I bulleted here? And if you did, then you're gonna get full points. Okay? So let me give you your surfaces.
Are we allowed to ask you for those?
I have wood and wood.
Do you think we're gonna have time to finish this in class?
You will finish all of your measurements in class because all you're doing is lifting and recording angles 5 times. You might not have time to finish your write-up.